So we've done the sum and difference rule, which was adding and subtracting. And the nice thing about the sum and difference rule is we could just take the derivative of each function separately and then just add them together in the end. So it was really no more difficult than anything we'd done so far. Now we're going to get into the product rule. What happens when you multiply two functions? So now coming from the sum and difference rule, most people will think, well, if I just do the derivative of them separately and added them when I added and subtracted, when I get to multiply, my gut reaction is, why don't I do the derivative of both of them separate and then just multiply them together? So a guess might be, well, the derivative of my first set of brackets will be 3x squared plus 3. The derivative of my second brackets will be 2x minus 5. Why don't I just try and multiply them together and see if it works? Well, that was Leibniz's first guess as well. He's like, well, let's try and multiply them together and see if it works. Unfortunately, it doesn't. And you can see that it doesn't if we take something that's much simpler. So suppose you had y equals x times x to the fourth. And if you did the derivative of each thing separately, the derivative of x would just be 1. And the derivative of x to the 4 would be 4x cubed. But we know that we can put both of those together to get y equals x to the 5, and the derivative should be 5x to the 4. So by taking a simpler example and trying our gut feeling, something that we knew we could do the derivative of, we found out that this is wrong, and in fact what we did here to begin with is wrong. So maybe you just say, well, maybe there is no way to do the product rule, but Leibniz kept working on it, and he came up with the product rule, which is a little bit more complicated than it first looks. But what it says, and we can see this a little bit better if we use some color coding, is if you have one function, which I'll color code in yellow here, multiplied by another function, which I'll color code in green, what we're going to get is the following. To get the derivative, we keep that first function the same. And then we multiply that by the derivative of the second function. Then we keep the second function the same and multiply that by the derivative of the first one and add those two together. That is in Newton's notation. If we use Leibniz notation, we've got one function u multiplied by another function v. And the derivative of that, you would keep that first function the same and then multiply by the derivative of the second one. Plus keep the second one the same and multiply by the derivative of the first one. Now, the order doesn't matter because we're adding. So sometimes as a memorization technique, some people just say, keep one the same and multiply it by the derivative of the other one. Then add whatever one you didn't keep the same the first time, multiplied by the derivative of the other one. So can you see that? You always keep one the same and multiply by the derivative of the other one. And then you're going to add the other one multiplied by the derivative of the other one. So what does this look like in an example? So we're going to solve this question using the product rule, and then we're going to solve this question using the sum and difference rules that we've done before. So I'm going to split this sort of in 2/3, 1/3, because the product rule takes a little bit more space. So using the product rule, we first have to see where's the multiplication happening. Can we see that we have the multiplication right there? And if I color code things again, I have my first function in yellow here multiplied by my second function in green. So the product rule says keep one of them the same, so if I keep the first one the same, and then multiply it by the derivative of the second one. What's the derivative of the second one going to be? Just 2. Plus, now I'll keep the second one the same, multiplied by the derivative of the first one, which is 2x. Now, if we weren't asked to simplify anything, this would be done. If we were asked to simplify things, well, this will be 2x squared. If I distribute this 2x all the way through, I'm going to get plus 4x squared minus 2x. Combine my like terms, and I get 6x squared minus 2x. Now, we could have done this question using our old technique. Can you see that you could multiply that x squared through? And if you take the time to do that first, x squared times 2x will give us 2x cubed minus x squared. And then we can use the sum and difference rule. We can just do the derivative of each thing separately. And notice we get exactly the same thing. So at times, you're going to look at your original question, and you'll have more than one option on how you could solve it. You could say, well, I could multiply this out, then maybe I could use my sum and difference rule. Maybe that makes it easier, and I think in this case, it looks like it did. But if I don't see that right away, I could also say, well, I have two functions multiplied together here, and then I could use my product rule, which says keep one the same, which we did here, multiply by the derivative of the second one, and then keep the other one the same, which we did there, multiply by the derivative of the first one. So as we get to the second one, again, you could multiply this all out. Now the multiplication might be a little bit more involved, or you could use the product rule. Can you see that the multiplication is right there? So this is our first function. I always highlighted the first one in yellow. Be consistent. There's our first function in yellow, and there's our second function in green. So write out the product rule. And how did you do? So we kept our first one the same right here, multiplied by the derivative of the second one. Then we kept the second one the same right there and multiplied by the derivative of the first one. And again, if it didn't ask you to simplify, this would be done. If you were asked to simplify, well, we'd have to distribute here, so we would get 6x to the 4 minus 14x plus, and here we'd have to multiply this all out, 24x to the 4 minus 12x cubed minus 14x plus 7. Combine our like terms, 30x to the 4 minus 12x cubed minus 28x plus 7. Now, the nice thing is often on quizzes, I won't ask you to simplify it completely. I'll just say, find the derivative, no need to simplify, so then you would just need to do the first line here. That would be enough. But as we do questions from the textbook, what's going to happen in some of those questions is I'm going to want you to make sure you check your answer at the back of the book. And if the answer is in a simplified form, I want you to practice your algebra skills to get it into that form. Because that's going to be something that's really going to help you in university, is practicing those algebra skills. Here's another one for you to try. Again, recognize where the multiplication is, and then use the product rule. Again, this notation just means find the derivative. This d dx means find the derivative of what you have inside. All right, let's see how you did. First of all, before I took the derivative here, I changed my square root of x cubed. That means x cubed to the 1/2, which will be x to the 3/2. And again, I have my first function multiplied by my second function. Now, what we're going to do here also, again, we kept our first one the same, multiplied by a derivative of our second one. Then we kept our second one the same and multiplied by the derivative of the first one. And this one I left like this. I didn't bother simplifying it further. Some things just to note as far as what do things mean. This d dx means it's a command derive with respect to x. So that d dx is a command that wants you to derive whatever's inside with respect to x. When we write our answer, dy dx, in short form we can say this is the derivative is, that's what dy dx. If we want to be more explicit, the derivative of the function y with respect to x is. So again, we'll try to make sure that we talk about what do different things mean, because if you know what they mean, it helps you understand further when you're doing more questions. So the derivative of the function y with respect to x is equal to what we found there. Okay, we're going to take some time in class to do some of these practice exercises.